Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Thank you for joining the Geoscience and Geoenergy webinar of today, 31st of March 2022. Today, we have the pleasure and honor to host our colleague, Professor Anna Scotti from Politecnico di Milano. Anna works as an applied mathematician in the Department of Mathematics at the Polytechnic of Milan. Since her PhD, her research has focused on the challenges in the numerical simulation of geological and geophysical processes, often in collaboration with industry. In particular, the main research interests of her are the study, development, and benchmarking of numerical methods that are robust in the presence of heterogeneous domains, complex geometries, and embedded interfaces, and also coupled multiphysics problems involving porous media flow, chemical reactions, and mechanical deformation. For more information about her research, please do visit her Google Scholar page. I'm going to post it in the chat box in a moment. And thank you, Anna, for graciously accepting our invitation to offer this lecture to the audience. Please note Anna's lecture will last for about half an hour, followed by questions and discussions. Like always, please do type your questions in the chat box. Christine will kindly co-chair this session in the question and answering part, so she will highlight your questions and ask Anna about them, and so we will hear Anna's comments on them. Without any further ado, the stage, the bandwidth, is all yours. Anna, thanks once more. We are very much looking forward to hearing your talk.
Hi, good afternoon, everyone.
Anna, we yet do not see. Yes, perfect.
Yes, perfect. Yeah, thanks a lot, and good afternoon, and thank you very much for inviting me. It's a pleasure to be part and an honor to be part of this series. And yeah, my talk, after submitting the title of my talk, I realized it was a bit too probably generic. So it is about mineral dissolution and precipitation in fractured porous media. And then I thought I should also probably add that I'm going to talk about, say, mathematical modeling, numerical methods, and some experiments that we did with uncertainty quantification methods. And so before I start, I should acknowledge my collaborators so that you know that what you will see is not my fault alone. So Alessio Fumagalli and Luca Formaggio from Politecnico di Milano has worked with me for a long time on the modeling and simulation of fractured porous media. And Michele Botti, who is currently a postdoc at Politecnico di Milano, has worked on the uncertainty quantification part in this presentation. And then Simone Ripamonti is a master's student who has been working very hard lately on the modeling of more complex reaction sets than the ones that we will see in this presentation. And yeah, so let me begin by describing what are the problems, the target applications that we had in mind that motivated our interest, our research. So we're thinking of the effect of mineral dissolution and precipitation in problems like geothermal energy production or CO2 storage in the subsurface. So, for instance, in the case of geothermal energy, we want to see if the injection of water with temperature and concentration of chemical species that differs from the formation could trigger dissolution or precipitation of minerals. Or in the case of CO2, we would like to check whether the changes in pH due to the presence of dissolved CO2 could enhance the dissolution of minerals, or also in turn cause carbon mineralization, so the subsequent precipitation of other minerals that contain carbon. This could also be beneficial in some sense to storage if these minerals that precipitate reduce the porosity and the permeability of, say, the caprock or the formation. And okay, in all this problem, fractures are really important, as you all know. fractures can have a major impact on subsurface flow, both when they are highly permeable and also when they are sealed and they act like barriers for the flow. So if we have some mineral dissolved in the water, some reactants like CO2, their distribution is strongly affected by the presence of fractures. And when these reactants are advected and transported in the domain, they may react, and probably they will react close to the fractures, and they might change the material and the hydraulic properties of the porous matrix and of the fracture if they change porosity and fracture aperture. So this is what we would like to study. Now, of course, fractures are thin regions embedded in the porous medium, and so their aperture is way smaller than the typical domain and their lateral extension. So what we will do is model them as lines embedded in a two-dimensional domain or surfaces embedded in a three-dimensional domain. And this is a classic approach and will allow us to avoid the extreme mesh refinement that you see down here. So if we apply this geometrical reduction, let's consider the core part of our mathematical model, which is, as usual, the Darcy equation. This means that we will, from now on, solve a Darcy problem in the bulk porous medium, which is the usual Darcy problem. Here is written in its mixed form. We have Q is the Darcy flux related to the pressure gradient. And then we'll have a similar problem on the fracture, so on the tangential space of the fracture. And the two, of course, are coupled together by some coupling conditions that tell me how much flux is exchanged between the fracture and the surrounding medium based on pressure differences and the fracture permeability. So this is our starting point for modeling the effect of fractures in the subsurface. And it's not new, but however, the problem that we want to tackle today is way more complex. It's a multi-physics problem because Darcy is just the starting point. So we have the flow problem, which is, we consider a single phase flow problem. So if we have gas, we assume its concentration is very low, so it's dissolved. The solution of the Darcy problem gives us the advection velocity that transports our species in the domains and in the fracture. And these chemicals can react if temperature is large enough. So we also need to take into account temperature in our model. And finally, if these solutes react, they might change porosity, permeability, if they form a mineral or if they dissolve a mineral. So we have a feedback on the flow problem and on transport. So everything is coupled. However, the way we choose to solve this problem for reasons of computational efficiency, simplicity, is with a classic non-iterative splitting of the problem. So basically it means that for each time step, what we do is we solve flow, so the Darcy problem with the fractures. I obtain the velocity, and I use it to solve the transport of chemicals and temperature. And then we move on to solving the reaction step, which is usually a bit more complex because it can be nonlinear. And then once I have, say, the new mineral concentrations, I can update the properties of the porous medium. So of course, this splitting is very convenient, but it also, we are aware that it introduces an error, and this error should vanish as the time step of my simulation decreases. And this is what we try to check before moving on by comparing the solution with a fully coupled monolithic solution in a very simple case. And what we found is what you see here in this convergence plot is that the error decreases nicely as expected, except for the cases where the Dam Kohler number, the blue line, the Dam Kohler number is the smallest, which is the case with a higher advection velocity. So in this case, extreme cases, as expected, a very naive splitting like this could not be trusted. But other than that, we rely on this simple iterative splitting. And so what kind of reaction will we model? So we will consider a very, very simple model where we just have two solutes that are in these reactions called U and V, and those may react and form a precipitate that is in this chemical reaction called W, and in turn this precipitate could dissolve and form the solutes U and V. Now we know that if we assume that there's electrical equilibrium if U and V are two ions, then it's enough to keep track of the concentration of only one of the two to simplify things even more. So if we look at this diagram here, where the solute is on the x-axis and precipitate is on the y-axis, what happens is that if the solute has a concentration above equilibrium, then it will dissolve, so decreases concentration and form more precipitate. On the other hand, if I have a low concentration of solute, the precipitate will want to dissolve and form a solute. And then there's a critical concentration where I have equilibrium. And in general, the speed of this reaction is modeled as something that depends on the concentrations and on temperature, of course. So a high temperature in general enhances the reaction rate. So for what concerns the solute concentration U, so one of the two ions, what we need to solve to track its evolution is an equation that looks like this, and it has an advection contribution, so the Darcy velocity moving the solute in the domain. Then there's some molecular diffusion, and then there's a reaction term here written on the right-hand side. So it's a partial differential equation. And so the solute moves and reacts. Whereas for the precipitate, this is immobile, so it doesn't depend on the advection term. It's just, it evolves according to the reaction term. So its equation is just, say, an ODE, an ordinary differential equation. And also it can be solved locally in each cell if we treat reaction explicitly, which is very convenient. And what you can see is that the reaction term for these two is the same, just with opposite sign, because one grows at the expense of the other, of course. But because we are considering fracture, porous media, one equation is not enough, so we have the transport and reaction equation in the bulk domain, and then we have a similar one down here that gives me the evolution of the concentration of U in the fracture. So it's similar. We have advection, we have diffusion, we have reaction, and then there's an extra term that tells me how much flux of concentration is exchanged between the bulk medium around the fracture and the fracture. Just like before, but the coupling conditions are slightly more complicated because we have advection and diffusion responsible for this concentration exchange. And finally, the last ingredient would be the fact that the changes in mineral amount that we observe impact the porosity. So if, say, Phi-W is the reactive volume fraction, so the volume fraction of the precipitate W, and we have also an inert volume fraction, then we can obtain the porosity as a difference. And also, if we know the molar volume of the mineral, we can directly relate the porosity to the mineral concentration. And once we have it, we can also update the permeability with, say, a Kozenic-Karman type of law that tells me how permeability changes as a function of porosity. Similarly, the formation of precipitate can also reduce the fracture aperture, and we would use a similar law, so the decrease in fracture aperture will be somehow proportional to the amount of precipitated mineral. And then based on the aperture with the classic parallel plates formula, we can update fracture permeability. And yeah, so all the results that I will show today are computed with the library PorPy, which is an open software in Python for the simulation of porous media. And the discretization method that we use is quite simple, since in this case we consider classic triangular grids that are fully conforming to the fracture. And for what concerns, say, space discretization, we use lowest order mixed finite element for Darcy, so we have a nice approximation of velocity, and finite volume with an upwind flux for the transport problem. So a first result, and before moving on to more complex stuff, is let's see if we consider a domain cut by one fracture and we have no flow boundary condition on the two sides. And on the bottom boundary, what we impose is a higher temperature, a higher pressure with respect to the initial condition, and a solute concentration that is above equilibrium, so that we will trigger some precipitation. And the fracture is initially open, so it's very permeable. After a few steps, what we see is, so down here we have what the pressure and the velocity field looks like. We have pressure that starts diffusing, and we have the solute infiltrating the fracture and a little bit of the porous medium around it. And the solute starts precipitating in the bottom part here. So we see a porosity and an aperture reduction in the bottom part of the domain. And after some time, this precipitation, this porosity reduction, has an effect on pressure because the fracture becomes impermeable, and we can clearly see a pressure jump here and the corresponding substantial reduction in porosity that is stronger in the bottom part of the domain, where I have higher temperatures and more solute. Yeah, so then we thought we would like to sort of quantify the effect of transport speed versus reaction speed. So in other words, what happens if we consider different Damkohler numbers? So if the Damkohler number is the ratio of reaction rate and advection velocity, so if it is small, it means that reaction is slow compared to advection. So if we consider these three plots represent a 1D case where there's solute injection in the center of the domain. So if reaction is slow, precipitation occurs more or less homogeneously everywhere, whereas on the opposite side of the spectrum, for a large Damkohler number, fast reaction, the solute cannot travel very far before precipitating. So we see that the effect is just really focused around the point of injection. So we thought, if we consider a fracture that transporting the solute, does it make sense to think that for a fast reaction, then precipitation will be probably focused into narrow region around the fracture? And if they are really thin, does it make sense to model them just like the fracture as something that is lower dimensional, so a line? So in other words, if we look at this picture, and if these yellow regions around the fractures are really thin, we will try to model them as lines around the fracture in a sort of sandwich-like model. So yeah, we tried. We have a fracture, which in principle has a thickness, but it becomes a line. And then we have around it these two blue layers that I call reactive layers, and they are denoted by this letter mu. And they also become lines. And these lines have their own thickness, their own aperture, but they are geometrically the same lines. So what does the model look like now? More or less like before, but we have also a reduced equation in this extra lines on the two sides of the fracture. So we will have a Darcy problem in the reactive layers, and also a reduced transport problem in the reactive layers. And these reactive layers have their own porosity, their own concentration, and they exchange fluxes with, on one side with the fracture, and on the other side with the rest of the porous medium. And the only missing part in this model would be what is really the aperture, the thickness of these layers, because not only it is unknown, but it's also something time dependent, because in the beginning of the simulation, this aperture could be 0, and then it could grow as the mineral precipitate due to the solute flowing out to the fracture. So the missing ingredient in this model would be a model for the layer thickness, the reactive layer thickness. So what we assumed is an idealized case, no doubt, where there's a flux exiting the fracture in the normal direction, more or less, and it is fairly constant. So the concentration of solute in the fracture, I see it as a boundary condition. And then I try to solve a 1D problem, a 1D transport equation with the value in the fracture as a boundary condition. And so it's a transport reaction problem. And if reaction is really simple, like linear, one can also obtain an exact solution so that we have the solute profile close to the fracture, like in this picture here. And then if I set a threshold, let's say that if the solute has a concentration below a certain value, then precipitation is basically negligible. So if I set this threshold, I can find the corresponding thickness of the region that is affected by precipitation. So this gives me a time-dependent law for the layer aperture. So we plug this in our model, and then we try to check if it makes sense, if results make sense. And how? So we take more or less the same geometry of the previous test case. And what we did is we simulated this sandwich multi-layer reduced model and compared it with one that is equidimensional on a very, very fine grid that is able to resolve this solute profile, and we compare them. So once again, we have solute entering the domain from the bottom and flowing in the fracture and flowing out of the fracture. So yeah, the solute distribution will look something like this. If reaction is fast, it's really focused close in a region close to the fracture. There's a bit more of a 2D effect only close to the tip. So now we plot the solute profile along this dashed white line. And the blue line that you see here is the solute profile computed with a very fine grid, so it's the reference. And then if I set my threshold delta to be, for instance, 0.1, so, and I compute the corresponding thickness of the area where, in my opinion, precipitation is relevant. This is represented in this picture by the green dot and the green triangle. So there's a fairly good agreement. So it seems that the prediction makes sense if we are in the assumption of the model. And we also compared what it looks like in time. So in this plot here, you see that the red line is the thickness that we compute. So the evolution, the time evolution of this region computed with a very fine grid. So it grows in time until it reaches its steady state value. Whereas the blue one is the one predicted with our, say, reduced analytical model. And it's not too bad. So the steady state value and also the time evolution match reasonable. So we think that, okay, it's a promising strategy that allow us to save a lot of computation by avoiding extreme mesh refinements, but of course it's still very simple. So it should be extended to more general behaviors where we have both precipitation and dissolution, switching behaviors, and so on. And the other point that I wanted to make is that all the results that you've seen so far, and you probably noticed, are obtained with synthetic values of the coefficient that are not, of course, realistic. And the point is, realistic data are, of course, available, but they're also affected by variability and also a lot of uncertainty. So this is the third part of our work, is to assess the effect of such uncertainty on the solution. So for instance, we usually have uncertainty on initial and boundary data, on the chemical composition of fluids and rock, and also a lot on the reaction rate of our reaction. So not only I want to apply an analysis of variance to assess how much this uncertainty affects the solution, but also because, as I will try to show, this type of analysis gave us a lot of insight in the problem coupling. So it gave us a very interesting angle on the problem. So we try to implement a UQ workflow where we selected a small number of uncertain parameters, and then we decide their range and we sample the parameter space. And we did not use a Monte Carlo sampling, but we chose to use a sparse grid sampling. So we work with grids that are not fully tensorized, so we save some computational time, so we're more efficient. And for each point on this grid, so for each combination of the parameters, we have to run a forward simulation. We'll see later how many. And then we work with the output. We compute a polynomial chaos expansion to obtain two things. So one is a surrogate model, so a polynomial model that is fast to evaluate and kind of can be used as a surrogate of the complete model. And we can also compute statistical quantities. So in detail, let's say that C are our uncertain parameters, then the model output depends on this parameter, and we express the model output X as a series of polynomial, and then we chop this series, reducing it to a finite dimensional expansion. And with the coefficients of this expansion, we can compute, for instance, the mean of the porosity that we have here, the variance of the porosity, but also, that is really interesting, the Sobol indices that tell me what is the impact of one of the parameter on the variance of the solution. So the first interesting thing is that even with a relatively coarse approximation, we obtain that the porosity obtained with approximated with the polynomial chaos expansion looks very similar to the true one. So the relative error that we have was only of 5% at most, and this is really nice. Of course, the problem is simple. And then we also checked that the error decreases as we enrich our approximation. So in this case, what you see is how the error on porosity, solute, concentration, and so on decreases as I add more and more layers to the grid that I use for parameter sampling. So a richer approximation. And so the uncertain parameters that we consider are the temperature at the bottom as a boundary condition. And then we wanted to have uncertainty. Of course, there is a lot in the reaction rate. So we chose to have an uncertain activation energy. So this lambda would be the reaction rate that is then multiplied by the concentration to obtain the reaction speed. And then we also consider as uncertain this coefficient eta, which is somehow proportional to the specific volume of the mineral and tells me how fast a fracture aperture changes as I have more and more precipitation. So with three uncertain parameters, the cost as we increase the number of levels on the sparse grid is what you see in this table. So for the coarser is 31 runs, and then it grows, of course, with the levels. And yeah, it's important that it's not too out of control because each one of our runs is two-dimensional and it's time dependent, so it takes a while. And yeah, then we can see some results. For instance, this is the partial variance of the porosity. So my quantity of interest is porosity, and I want to see how it is impacted by the uncertainty in the activation energy. But I can also see where it is impacted and when, how does it change in time. So this quantity depends on space and time. And early in the simulation, I see that the maximum impact is in the bottom part of the domain where I have the inflow and also where temperature is high, things are happening. So where there's a lot of precipitation. And then, for instance, it's already interesting to see that later on, the maximum partial variance is in this part of the domain, and we wondered why. And we think it's because towards the end of the simulation, the fracture is completely blocked. So flow in the transport of chemicals have to circumvent the fracture from the right. And then one can also look at the correlation index, for instance. And so what you see on the left is the correlation index of porosity and precipitate, for instance. And don't be fooled by the colors. The scale says that it's -1 basically everywhere. And it makes a lot of sense because porosity decreases if precipitation occurs, so fine, easy to interpret. And also, if I check the correlation of solute and precipitate, it's -1, so negatively correlated more or less everywhere. And this also makes a lot of sense because one grows at the expense of the other. And yeah, it's already a bit less trivial if we see the covariance of porosity and temperature, for instance, because it's negatively correlated in the bottom part of the domain and positively correlated in the top part. And say the switching point changes in time. So this is an early point in time in the simulation, and this one is later on. And this is already less intuitive, so we thought about it. And on one hand, temperature favors precipitation, so it tends to reduce porosity. On the other hand, the problem has so many couplings in it that temperature is also affected in other ways by porosity because there's, for instance, thermal conductivity depends on the porosity and also in a nonlinear way. So the overall effect that we see is determined by the interplay of many effects. So I think that taking a look at these quantities gives us a very interesting tool to try to gain a deeper insight into the behavior and the couplings of our model. So if I have a few minutes, just a few words on what is really ongoing work, just a few pictures. So what we're trying to do now, there's a master student who is finished this thesis right now, probably today. He has been working on trying to include into this framework that we have more realistic reaction schemes. So what we're trying to do is to account for some CO2 dissolved in water, which forms carbonic acid, which changes the pH. And this acidic water enhances the dissolution of minerals. So we have combination of equilibrium and kinetic reaction this time, which is a bit more difficult. And yeah, so he worked with the classic total concentration formulation and tried to see how the presence of different fracture configuration can impact the results if we have, say, an inflow of CO2 and low pH from the left of the domain. And of course, in this case, where fractures are impermeable, the pattern of the CO2 flowing into the domain is affected by these barriers, and also the movement of the products of dissolution, calcium, is impacted by the presence of fractures, and as a consequence, I have a lot of dissolution of mineral, not really a lot, but more dissolution of mineral on the left part, and way less on the right part. And if fractures are conductive and parallel to the flow, like here, then of course it's completely different effect. So this is ongoing work. To wrap up, what I try to show is our model for say, simple model for reactive flow with fracture, where fractures are lower dimensional objects with an aperture that can change in time. Then we also made this attempt to simulate narrow reactive regions around the fracture as hybrid dimensional domains as well. And it works, but it also needs a lot of work to be improved and generalized. And then what I wanted to show is how uncertainty quantification can be really useful, not only to assess the sensitivity of results, but also to try to dig into the complexity of and the couplings of a multiphysics problem. And what I see as future necessary developments of these works, what I would like to be able to do in the future is use realistic data and more realistic reaction networks. And also, in this case, I think it would be really beneficial to have an implicit fully coupled discretization, because it would be more robust in general cases. Yeah, so thank you very much for your attention.
Thank you very much, Anna, for this very interesting talk. I see plenty of questions already posted. So, Christy, please take it from here.
Yes, thank you very much for the great talk. I have a couple of questions on my own, actually. I'm not sure if I will have the time to ask them. I guess I'll start with some technical questions first. Yuhan Wang is asking, hi, Anna. Karman-Kozeni's formula has porosity squared over 1 minus porosity to the power of 3 relationship. Is there any reason you assume only porosity squared part?
Yeah, okay, no, you are absolutely right. So what I was showing there first is is the ratio of 2 permeabilities. So one is in a reference condition, and the other one is the new one in the actual present condition. So what I have shown is sort of the ratio of 2 Kozeny-Karman formulas, where I'm also neglecting the denominator because it's almost 1 in both cases, something like that. It's an approximation. I think it rather models the change than the value itself. I hope it was clear.
Okay. Yeah, good. There's another question from Rolling Hills of North Wales about the fracture aperture evolution. Is there any upper limit to the aperture size, or how open can a fracture be initially? Or also like after dissolution, I guess.
Yeah. From a physical point of view, I guess at some point the model that one should consider should change. So if it's a very wide fracture in some sense, then one should not use a Darcy type of model, but rather Stokes or Navier-Stokes or also account for nonlinear terms in the flow model. And from the numerical point of view, from the point of view of the discretization that I use, so having a reduced model where the fracture is aligned, from the purely numerical point of view, is something that makes sense if this aperture is really small compared to the grid size that I use elsewhere. Otherwise, it doesn't really make sense.
Okay. Now that you're talking about a grid, I'm taking the question from the second question from Yuan Wang. When dispersion is considered, mesh should be very fine, so the numerical dispersion does not overrule the physical one. Can you comment on how to choose the mesh resolution appropriately?
Yeah, okay, that's a good point that you're making, because I have only mentioned this, say, magical coefficient, not even tensor D, and I just said that it's diffusion, but of course, if you want to also include dispersion in there, so if you wanted to account for the effect of non-negligible velocity, and it's a completely different story. And then it is true what you said, that I cannot have an arbitrarily large mesh around the fracture. So even if the fracture is lower dimensional, I should take into account the gradients of the solution to be accurate. So for your specific question, I don't know because I never model dispersion in my problems. I just had a very small diffusion for molecular effects and so on. But it is true that mesh solutions should not only be based on geometry, but also on the quality of the solution, of course.
Okay. Then I take a question from Florian Doster. Thanks for the nice presentation, Adam. Do you also consider how the precipitate in the fracture might impact the interaction between the fracture and the porous media?
Well, okay, no, but it's really, really interesting. So it's kind of a gray zone there in the modeling where one doesn't really know if the precipitate that is precipitating is on the walls of the fractures, whatever they are, or it's just in a thin layer just at the boundary between the fracture and the porous medium, and if it could like make the fracture walls impermeable. So I don't, but I really would like to study this at a fine scale. And if you have any suggestion, we're really interested.
But at the end, you look into the permeability change. So at some point, you can get a permeability of 0. So
yeah,
to a certain degree, you do look at it, I guess.
I do in some sense. So if the aperture of the fracture decreases, because I use this parallel plate formula to have the conductivity of the fracture, I account for the fact that the fracture becomes impermeable, but not, this changes the normal permeability of the fracture as an overall effect, but I'm not looking into, say, this fine scale problem and what happens at the boundary. So I'm just assuming that this precipitation is attached to the fracture walls, and so the fracture is thinner and thinner and thinner. So in the end, yes, its permeability can almost drop to 0.
Okay. He also asks you about boundary conditions. So somehow I missed the boundary conditions in your main example. Did you impose flux or pressure drop, or did you explore both? And I guess what would be the difference be then?
Sure. For the pressure, it's so it's a pressure drop from top to bottom or bottom to top, and it was no flux on the sides. Yeah, of course it would change. And then for the temperature, it's prescribed at the bottom, and then it's and then what? And the solute was I had a boundary condition for the solute at the bottom. So if the velocity was entering, a solute concentration was entering. So it was a pressure drop.
Okay. Then let's talk a little bit about the layers. And another question from Florian. Have you thought of making the layers adaptive? The change in precipitate might change the flow properties. That is, the Numerical number and hence different approximations might be appropriate during their evolution. I guess this also relates to how the precipitate is interacting with the matrix. Huh?
I'm not sure I know what you mean by adaptive. So at the moment they are, okay, what I'm assuming is that they are always thin enough that I can represent them as line, but their thickness is changing in time, and their porosity is changing in time, and their permeability is changing in time. What I think is more difficult, but not impossible, but I wouldn't know how to do it like today, is to have them to have a model that's so general that they can be modeled as equidimensional or lower dimensional depending on the situation. So I don't know.
So yeah, he says also, thanks for the answer, Anna. I do not have any immediate suggestion, but happy to have a chat anytime.
Sure, thank you.
That's great. So a question from Anne-Laure Tertois. Thanks for an interesting talk. How do you think this Python code would scale to 3D models, both in terms of complexity and performance?
Sure. Now I'm sorry that I regret not adding a 3D simulation. So it does work in 3D with, but of course the cost will grow. So it's not a problem if you have to run a deterministic model. It works perfectly. The only thing is for the uncertainty quantification part, it will probably take a long time. So we should run it on a parallel machine. But then the task is inherently parallel, so it could be done. It hasn't been done yet.
Staying with the numerics here, a question from Kirush. Could you also comment whether you solve flow equation explicitly or semi-explicitly? If yes, I wonder why not fully implicit coupling.
So the flow problem, Darcy problem, is solved. So it's not really time dependent in a sense that I don't have a pressure diffusion term, but I do have say a time dependency in Darcy due to the fact that porosity changes, and that part there is treated explicitly, just because the problem would be completely coupled, but in my, say, non-iterative splitting, I have to approximate the derivative of the porosity with previous values. But then if you assume that this porosity change is slow enough, it's not a huge deal. Whereas instead, if for the transport equation, the transport is implicit, but the reaction part is kept explicit because it is, for two reasons, it is nonlinear. So this way I avoid nonlinear iterations with Newtons and so on. And also if I have many concentrations and I keep reaction implicit, this would couple 2, 3, 4 transport reaction problems together. So for reasons of cost, reaction only is explicit and transport is on the left-hand side.
Okay, thank you. This question from Antella Kane. Thank you for your talk, Ada. Why porosity change is localized on the right side of the fracture, not on the left upper part? Are there any gravity effects of flow, or is it lithology driven?
On the right-hand side of the fracture.
Yes, so it was like localized on the lower side of the fracture.
Oh, okay. Yes, on the right. Yes. So that problem is, it is. It looks vertical, but there's no gravity. First information, so you can think of it as something where we look from the top, so in a horizontal plane. And the reason why the effect is higher there is because first there's solute inflow is from that boundary, so we are closer to the boundary condition, so the concentration of solute is higher, so reaction is faster. And also we are closer to the boundary condition for the temperature, so it's also hotter there, so reaction is also enhanced by that.
Okay. And there's a question from Po Wei Huang. Thank you for the interesting talk. What are the species considered as primary variables in the CO2 dissolution case? Do you consider different diffusivity for each of the chemical species?
Mm-hmm. Okay, so I know the diffusivity there is the same for all. And I think what we did is we expressed HCO3 as a function of the other species using the equilibrium equation. Then again, it's a work in progress, so I think we should. I'm not really sure that we included all the aqueous equilibria that we should have. So, but for considering the equations that you saw in the slide, then it's HCO3 that is functions of the other in our formulation.
Okay, and another question from the audience, if I still have time, from Kiarash. I guess also about more like future work. Pressure drop may cause degassing of dissolved gases. What would be the main challenge taking into account two-phase problem?
Okay. Yeah, it's true. So what I said is part of the story. Of course, I said if the concentration of gas is low, then it is dissolved, but it also depends on on the pressure and temperature conditions that you have. So yeah, we haven't taken that into account. So the challenge there would be, I think, the main challenge to have a reliable thermodynamic model for mass exchange between phases and for computing the composition of phases. From my other experiences, this is a very tricky point.
Okay, I guess these are all questions. Thank you for the audience for the great questions. I will ask my questions afterwards because of time limits, I guess.
Yeah, okay.
Okay, thank you very much, Christine, Anna, and all the audience for the great questions. I'd like to also take the chance to introduce our next week speaker. Next week, we will host Professor Sarah Abedi from Texas A&M. Sarah will give a lecture about chemomechanics of shale rocks at the microscopic length scales. So until next week, the same time, 4 p.m. Central European. Stay happy, healthy, and tuned in to our channel. And we wish you all the very best until next week. Thanks a lot, Anna. It was a wonderful lecture. Thank you.
Thanks a lot. Bye-bye.
Thank you,
Thank
everyone.
you.